Hi, everyone. My name's Jeff Kiske. I'm the CEO and co-founder of Engin ML. And Engin ML, what we want to do is we want to help companies that are doing deep learning scale beyond the 4 GPU training that you're used to when you buy a box and put it under your desk. Before starting Engin ML, I was a master's student at Stanford working in Andrew Ng's lab doing deep learning research for self-driving vehicles. I co-founded Drive AI. I then joined Auto as a machine learning engineer, and then went to Uber doing deep learning object detection and 3D recognition for things like vehicles, bicyclists, and lane lines. So I believe that we are in a winner-take-all race for progress with deep learning. For self-driving vehicles, there's a bunch of analysts that have said that the first person that can deploy a self-driving vehicle will be able to capture a $100 billion, maybe a $1 trillion market, or multi-trillion-dollar market. And being able to get the first car on the road as fast as you can is super, super, super important. So this is why you have so many companies trying to work towards this. And this is why I was so excited to work at all of these different self-driving companies. I also believe that it's a race to save the environment. Google, a few years ago, released a paper where they were able to reduce their energy consumption in their data centers by around 40% using research from their DeepMind laboratory in London. And you know, if you reduce the energy usage in your house, maybe you'll save $100. But when you're at Google scale or Amazon scale or Microsoft scale, that's very, very important and amounts to millions, tens, hundreds of millions of dollars a year. And finally, I believe that deep learning will help us save lives. When I was at Stanford, I was working with a couple colleagues that were doing deep learning detection of skin cancer. And during the process, they were able to detect skin cancer on patients using just a cell phone camera better than board-certified dermatologists. So you can imagine a scenario where you deploy this out to everybody in the world, people that don't have access to dermatologists readily, and they can easily detect skin cancer way before they need to go see a doctor, and they can get the treatment that they need very early on. So getting to this point is very, very important, and all of these problems can be solved with deep learning. So I'm going to go a little bit into the weeds now and talk about where we're at today and how things have changed over the past few years with machine learning. So up here's a slide. I put together some of the most recent examples where people have trained what's called ImageNet. ImageNet's a data set of 14 million examples. There's 1,000 classes from horses to different types of breeds of dogs. And right now, we're at superhuman levels of accuracy. And generally, what that means is you're at about 75% accuracy top one. So the most recent examples that you've seen come out of places like Facebook and places like Google are like maybe top 5 accuracy of 3% error rate, but most of the time when we look to say when this problem is solved, it's 75% accuracy top one. So in the top left corner, you'll see a few papers that you may have seen before. There's things like Inception, there's things like ResNet, and then this 5-day one right here is ResNext. And so around this time, back between 2016 and 2017, most people were training on a single machine under their desk. So for example, this 10-day one is ResNet. It took 10 days to train on 8 GPUs. Facebook was then able to cut that time down by modifying their model a bit, but it still took them 5 days to train their model. And when you're in machine learning, you know how hard it is to know if your model is going to do better right when you kick it off. So you're basically starting a job, you'll come back a week later and try and figure out if that model actually performed better. A few months later, another group at Facebook released a paper called Training ImageNet in Under an Hour. And what they were able to do is take that 8 GPU workload and split it across 500 GPUs, 1,000 GPUs. And they were able to shrink that time down to train that model by 120x. And so since then, people have been able to shrink that down, now most recently by I forget who it was, but down to 3.5 minutes. Sony, by 3.5 minutes, and that was just at the end of last year. So another thing to note about this slide is every bullet point on this comes from a Fortune 500 company. And what we want to do at EngineML is make it so it's possible that so anybody can be on this slide, anybody can train their model in less than a day. This is super important, going back to my previous slide, when you want to get your self-driving vehicles out faster, when you want to reduce energy in your data centers, and when you want to detect cancer and improve the world. So let's see. So a lot of people have a hard time quantifying what a 100x speedup looks like. If I say things go 10x faster, a lot of times you can get to the point and you'd be like, oh, 10x is, I can understand that. But 120x is something that's very, very hard to fathom. So I put together a quick video of what that looks like. And all of this was done using EngineML. So let's see if we can get this to go. Real quick, this is a model called AVOD. It was at the top of the Kitty leaderboard for some time. It uses LiDAR data and camera data in order to detect things like vehicles, pedestrians, and bicyclists in the road scene. Kitty is a data set that's composed of 1,800 examples of those different data sources. And the goal is to be able to detect these things with a certain level of accuracy after the experiment is done training. On the left side, we have us training this model AVOD on 1 GPU. And on the right side, it's trained on EngineML using 128 GPUs. And this is the 128x speedup that you'll see. Cool. So every time a line is printed out, this is it seeing 128 examples of your data set. On the right side, we just completed one iteration, or an epoch, depending on how you say that word. But generally, you want to get through 60 or so, maybe 100 epochs through your data set. Especially on a small data set like Kitty, you may want to train for a lot longer. On the left side, we still haven't even done 128 examples yet. We just got there. The right side will take you 2.5 hours to complete training and be able to have your model up to that accuracy that you would want. And on the left side, it would take you 2.5 days. So you can imagine starting this experiment before lunch, taking a long lunch break, getting a coffee, and coming back and having your model completely trained so that you can iterate really quickly and go on to your next experiment that you want to try out. The model on the left, it requires a weekend. It requires you to take some of your resources. Maybe you have 4 GPUs under your desk, and you're now using one of those GPUs for 2.5 days. And so it's a non-starter for a lot of companies, but this is the world that people live in for most of the time, because getting to the point where you can train on 128 GPUs is difficult. Cool. So speaking of difficult, there's a bunch of people who I've talked to that have really struggled getting to the point where they can go from 1 machine to N machines. Oftentimes, 1 machine means 4 GPUs. On Amazon, you're able to train up to 16 GPUs. But going to that 17th GPU or to that 5th GPU is very, very challenging and requires a lot of work to do. I've talked to a bunch of my friends. Most of the time, they're happy. They do their 4 GPU training, but it still takes them about 5 days. And I just found a quote from the machine learning subreddit. I'm interested in getting multi-node, multi-GPU into my workflow, but PyTorch distributed data parallel is bewildering. And I'm sure some of you that have been doing machine learning have gotten to this point where you've scaled up to 4 GPUs, but getting to that 5th GPU is very, very difficult. So I want to chat a little bit about the best practices in order to go from 4 GPUs to 5 GPUs up to 128 GPUs. There's really only one way to do that right now with software, and that's a nickel-based ring or hierarchical all-reduce. And I'm not going to go into the details about how all that works. Just know that it's very efficient. It scales out to about 90% efficiency. So when you're training on 128 GPUs, you're going to get around 110x scale-out. There's some other different techniques you can use. Some people might have heard of parameter servers. Those scale out to somewhere around 60%. And these are things that are generally built into frameworks like PyTorch or frameworks like TensorFlow by default. Nickel-based ring all-reduce was popularized by Baidu in 2017 and eventually was ported into frameworks that you might have heard called Horovod, which was released by Uber in late 2017. And the scale-out of these frameworks is super impressive, and it allows you to very easily scale things out. Now, the infrastructure world is not the same. Whereas there's kind of one best practice where you would allow yourself to distribute your model on 1 machine, when you want to go to multiple machines, it becomes very difficult. And this slide just captures some of the different trade-offs you have to choose when building out your distributed machine learning pipeline. So I want to highlight one of them, storing and fetching data. Amazon offers a couple different types of services and ways for you to save your data on that machine, or in the cloud. You can save your things on EFS, which is Amazon's equivalent of an NFS-like file store. You can save things on EBS, which are block stores, SSDs that get attached to instances. You can put things on FSX, which is Amazon's Lustre store. You can save things in S3, and probably most of you have your data in S3 already just as a backup. Or you can roll your own HDFS-type service and pull data in from that. Now, each of these have different trade-offs that you have to take into account when making a decision when you want to do distributed deep learning. If you choose something like EFS, you have very low latency when reading files, but you struggle with throughput when you are on many, many machines. So if you have 16 machines, 8 GPUs apiece, you have 128 GPUs reading in that data, then what can happen is you can get bottlenecked by that single pipe going to each of those machines. You can put your data on an EBS store. The problem with EBS is that you have to copy that data to each of those block storages before you can start training. So what that means, again, 16 instances. You'll have to copy your 1 terabyte data set to 16 different EBS volumes and attach those volumes. That can be super time consuming. And even though once it's on there, you have very low latency and very high throughput. So that works in the long run, but has a very high upfront cost. You can store things in Lustre or FSX, which is by Amazon. The issues with Lustre is that it's a transient data store. You can't be guaranteed that the data exists. It also struggles with throughput similar to EFS, and it's also much more expensive. So if cost is an issue, you may not want to do something like FSX. Most people already have their data stored in S3. The issue with S3 is that you have very, very high latency cost to pay when you're fetching data. So even though you can get great throughput, you can, if you've saved your stuff in big block stores like TF Records or in some other large data storage format, you can get very high throughput, and the latency doesn't matter as much. But most of the time, the people that we work with have their data stored in JPEGs, PNGs, CSVs. And so these really small files, they don't work with block storage like S3. And very similar, HDFS has similar problems where small files don't work very well. And so when you think about setting up your distributed deep learning pipeline, that's just one potential category of things that you need to think about. So there's other things like, do I want to run on Spot instances? Do I want to use Kubernetes? Do I want to use Docker Swarm, Mesos? And when you combine all of these potential different ways of setting up your infrastructure, you end up with this decision paralysis, and it's very hard to make progress moving forward. Again, tying this back to the beginning, the goal is to get it so that you can train your models very quickly. And if all of this stuff is getting in the way, it's very hard to get back to your original problem, which is maybe you want to solve self-driving vehicles or you want to do cancer detection. So this is all to say, this is very, very hard to get right, and it takes a long time. And even if you build something out, you may not have built it correctly. And so you pay a lot of upfront engineering time to just try these things out. So what did we do at EngineML to make this possible for people to get highly efficient distributed training without having to think too hard about how they want to set up their distributed training pipeline? I won't highlight all of these, but I'll talk through a few of them. We run on top of EKS, and this allows us to do cluster management, manage a lot of our services, and I'll talk about a few of those right now. So the first thing I'd like to highlight is our in-memory dataset cache. So I mentioned before, S3 has super, super high latency when you want to read data from it. The issue with that is you often pay a penalty every time you want to read your data set. And if you saw that example I mentioned before, you need to iterate through your data set maybe 60 times or so in order to get to the point where you can have your model fully trained to completion. So on each of the machines, we set up an in-memory data cache that is a read-through cache so that every time after the first read, you're able to get native speeds, SSD in-memory speeds, so that you're able to train your models very, very quickly on those machines. We're also able to predictively prefetch that data. For example, if you're training on 128 GPUs, you don't need to have your entire data set on each of those machines. You only need 128th of that data set. And so most of the time, that will fit inside an in-memory cache or on disk, which means that you can get those massive speedups without paying the latency cost of having your data on S3. Another thing I'd like to chat about is Spot Auto Restore. So most of you know what Spot instances are. They allow you to pay 75% of the cost of an on-demand instance. For a K80 instance right now, it's 90 cents per GPU per hour on an on-demand instance, and it's somewhere around 20, 25 cents on a Spot instance. Now, the problem is when you run on 128 GPUs and you're using something like Horovod, if any of those machines get preempted, the entire ring shuts down. You have to start training over. And if you haven't set it up correctly, you may have lost the most recent checkpoint. So what we've built into EngineML is a way to know when Spot instances are about to get shut down, automatically checkpoint the model, and then replace the Spot instance that's going to be preempted with an on-demand instance so that you can continue training, receiving the benefits of running on on-demand instances and the user experience, but also the cost savings when running on Spot. Finally, distributed debugging. When you're on a local machine under your desk, you may have 4 GPUs. A lot of engineers will open things like NVIDIA SMI or HTOP, and they'll keep track of their utilization metrics of their network and their CPU and their GPU. But now imagine trying to run each of those on 16 different machines, all with 8 GPUs apiece. It's pretty unimaginable, and it's very hard to keep track of how efficient these models are actually doing over time. So what we've built is a dashboard that runs on top of InfluxDB and Grafana that allows you to see your metrics of your training job over time. Now, it's not only important that you're able to see that your GPUs are highly utilized, but also be able to correlate that to the actual code that's running. So most of the time, you'll launch HTOP, NVIDIA SMI, and you'll see spikes in your GPU and network utilization and CPU utilization, but you won't necessarily know if your model is inefficient and at what points is your model inefficient. So oftentimes what we'll see is the CPU will spike, then the GPU will spike, and then the network will spike. And what that will allow you to notice is that maybe your input pipeline isn't set up correctly, and you should do better pipelining. So maybe you can fetch data while you're pre-processing the next batch, and also while you're training on a new batch. All of this is to say you can train a lot faster once you're able to know how inefficient your code actually is. And then this one is near and dear to my heart. I'm sure we've all been in a situation where we've left instances up over the weekend. One thing that I always dreaded was forgetting to shut those machines down and then going into work on a Monday and having to explain to my boss why I left $5,000 or $10,000 worth of instances running over the weekend. So with EngineML, you can always be certain that whenever a job crashes or finishes or you cancel it, those machines will automatically be deprovisioned, and you won't have to have these hard conversations with your boss to explain why you spent $10,000 over the weekend. So this is all to say that all of these problems are very hard to get right, and they're not your goal as a company. So if you're trying to solve self-driving vehicles, or if you're trying to do cancer detection, or maybe if you're trying to save energy usage at your data center, you don't necessarily want to have to worry about did I leave a machine up over the weekend? Or am I getting efficient throughput with my data over S3? And so we built EngineML to solve these problems for you. We make it really easy to interface. It's just about 5 lines of code change required. We have a very simple Git interface, so as an engineer, you don't need to know about what instances types you're running on, where your data lives, and you get all the benefits of EngineML without having to build these feature sets out yourself. So thank you very much. Open to questions now, and feel free to chat with me after.
All right, so we'll go for some questions.
Thank you for the talk. Most exciting part is, could you elaborate a little bit how to optimize my application code so I can I do not have to be bothered by the old MDOS law, even though there are 128 GPUs. But
sorry, optimize your code for.
To get around with MDOS law. MDOS law says you can only parallelize so much, and eventually the critical path will kill you.
Yeah, so generally we see scale out to around 1,000 GPUs. Anything beyond that, you get to the point where you are getting below a 90% scale out. So in practice, if you can train your model in about an hour, and that's if you're doing like 128 GPUs, most of the time that's enough. It's an open area of research in order to how to make this work. We have technologies like FP16 compression when sending data across the nodes, which allows you to reduce the bandwidth required to do training. There's also techniques like deep gradient compression, where you can ignore different gradients that may be lower than a certain threshold so that you can train faster and reduce the bandwidth as well. But in general, scale out to around 1,000 GPUs. You don't see performance degradation or scale out below 90%.
Do you see distributed learning across edge sites, like on-premise of a customer where they may have large data centers or large stacks, racks of servers? Do you see your EngineML running on each one of these different sort of racks of servers and doing distributed learning?
Right now we're focusing on cloud. We do have the ability, because we run on Kubernetes, it allows us to scale out to on-prem. We're a small company now, we're 7 people, and so we're mostly focusing on cloud providers. But there's no reason that technology like this cannot be deployed on-prem.
Hey, a few slides ago, it looked like it said gang scheduling. Is that a custom scheduler you all built internally? And if so, is there a reason you didn't use the native EKS scheduler?
Yeah, thanks for the question. The question is, why didn't we use the native EKS scheduler? So by default, when you're using Kubernetes, you'll use what's called ASGs, auto-scaling groups, to spin up instances. The problem with ASGs is that if you request 16 instances and there's a capacity limit, maybe you only get 10 at that time, you'll keep trying again to scale those machines up, but you're paying for those 8 GPU instance types while the other machines are spinning up. And so a lot of the people that we're working with would have maybe an hour or so where they were waiting for the next 6 GPUs to spin up, 6 GPU instances to spin up. And so we built a custom scheduler that uses what's called gang scheduling. And what that means is if I don't have enough instances at that time to stop and alert the user and prompt them, hey, do you want to continue using this, or do you want to try again in a little bit when maybe there's enough capacity? So the default EKS scheduler does not have that capability, and so we ended up building our own.
I think I have one question over here.
So if one were to use it, so the application has to be distributed, or you are going to distribute? For example, so do I have to have a distributed TensorFlow to use this, or a regular TensorFlow application, will you convert that to a distributed one?
Yeah, so we have a library that we've built that uses nickel hierarchical all reduce. It's about 5 lines of code change required. When I was at working at my past companies, we always got into this situation where you would have one code path for when you're training distributed and one code path where you're training locally, and that makes it really hard to debug when things go wrong. So we built the EngineML library. It uses best practices for nickel hierarchical all reduce and ring-based all reduce, but the benefit of using the EngineML library is code will run exactly as it would locally, except now it's on 128 GPUs in the cloud.
So one other question is that since in AWS, most of the instances are 1 gigi, not 10 gigi unless you have a multi-GPU. So you don't have, I think you answered the question, but I'm just asking one more time. So you don't have any network latencies when you have such a big cluster? Since the network is only 1 gigi, right?
Yeah, so I mentioned a bit before, there's ways to compress the gradients that you're sending. So your gradients might be 300 megabytes that you need to send at every step. If you can cut your gradients down to a 16-bit floating point representation and then send those over the network, now you've cut your bandwidth in half, which is really quite nice. But generally, we're bottlenecked by data throughput, not necessarily gradient updates.
Cool, we do one more question over here.
If I'm just getting started with deep learning and don't need 120 GPUs in the cloud, is there a way that I could use EngineML to get a taste of it?
So today, we don't have a way that allows you to scale from 1 GPU to 4 GPUs on a single box, but we're working on a system that would allow you to train and help you scale up if you are still struggling with going from one GPU to 4 GPUs on the same box. And that will be coming out in the next month or so. So if you are interested in running EngineML locally, you'll still be able to get the metrics dashboard and experiment tracking and all of the other services that we provide.